I want to start lecture B by emphasizing why the vectors in the vector field are velocity vectors for solution curves. It's based on the geometric interpretation of the differential equations. If you think of, again, the solution curve as being a curve that traces out, it's a parametric curve, it traces out a curve in the plane. Horizontal coordinate x, vertical coordinate v. dx dt is going to be, physically, the x component, the first component of the velocity. And dv dt is going to be the second component of the velocity. Why do those components have to equal this? Or why does the fact that those components equal these quantities, why is that reflected in the vector field? Because at any particular point whose coordinates x and v are given, for example, the point 2, 1, right about there, at that point, at a moment in time when a solution curve happens to be going through this point, the differential equations are saying the first coordinate of the velocity vector should be the v coordinate, the second coordinate of that point, 1. That's the x component of the velocity. Now, this arrow right there doesn't look like it's got a first component of 1. That's because it's too short. Make it longer, its first component would be 1. Make it the right length, its first component would be 1. What about its second component? You've got to plug the x and v, the first and second coordinates, into that expression. That's what I did with VectorPlot, is I plug these things in that list, separated by a comma. It's plotting those vectors based on these x, v coordinates at lots of points in the plane. And again, anytime a solution curve passes through that, at that moment in time, the first component of the velocity of the solution curve is the second coordinate of the point that's passing through. And the second coordinate of the velocity vector of that point is equal to this combination of the first and second coordinates of the point. Plug those numbers in. Let's just go ahead and do the example here. At the point x is 2, v is 1, to make this more clear. When x is 2, v is 1, what do we get? Again, go back up to what the vector field was. It's this. The first component of the vector field, I'll go ahead and write it as a list, as it is in Mathematica, is v. The second component is 5x minus 2v. Plug in v equals 1 and x equals 2. You get 1, negative 12. The true vector in the true vector field at the point x is 2, v is 1, has a first component of 1 and a second component of negative 12. So you've got to go down to negative 11 here. The true arrow for the vector field, for the true vector field, looks about like that at this point. The vector that's approximately right, one of these here, is essentially a scaled down version of what I just drew. Scaled down a lot. It's a lot shorter than it should be. If you imagine making a bunch of vectors like this all over the picture, you understand why it would be really messy to draw the vectors out the exact correct length. Let's go ahead now and review, for the purposes of reviewing these ideas, the concept of position vector, velocity vector, and acceleration vector. Let's put those vectors in this picture, even though you don't have to. Though the velocity vector will be very informative. Before I do that, I should say, by the way, of course you can, with these sliders, change the initial position and also change the initial velocity and get different solution curves. Well, they all spiral toward the origin. The origin is a stable equilibrium, actually. Let's add to this picture, again, a position vector, a velocity vector, and an acceleration vector. We did this near the beginning of the semester, though you may have forgotten how to do it. We used graphics and arrow. Remember using that? Graphics and arrow. The syntax is kind of weird, but here's the basic syntax for using graphics. You have the word graphics, capital G, you have the square bracket for its input. You're going to have curly braces inside there. And what goes inside the curly braces is things like thick, red, arrow. Then you specify the arrow. Then if you want a different color for another arrow, you put a different color like blue, and put another comma and put another arrow. Kind of weird. You can, again, you can always look up these examples in the documentation center if you don't remember how to use it. You can look up, probably the best thing to look is to look up arrow. And when you see arrow used in examples here, you see it's used inside graphics. Although if you just use an arrow, you don't need curly braces. But I'm going to add the other stuff like thick, red, blue, and so forth. So then I need the curly braces. Are there examples like that? Yeah, this example colors it. Adds in some arrow heads as well, but we're not going to bother with that. Thick. How about, let's make the position vector brown. Brown arrow. How do you make the position vector? Remember, position vectors of moving points are always based at the origin. So inside some curly braces, you first put 0, 0. Then you put the position vector itself, which is C. This thing. Except without underscores. Copy and paste this down there, except I'm going to want to change the T to a B, because the B is the thing that's changing in the animation. I need a B there so that my position vector moves with the curve as the animation parameter B changes from 0 to pi. I need a T up here because with parametric plot, you're plotting the function over a certain T interval whose right endpoint is B. I did mention all this stuff like, what was that, 2.5 months ago. There's your position vector. It's like it's a pen tracing out the curve, though I suppose I should have made it red then, huh? For color clarity. Let's go back and make it red. Let's add in a velocity vector now, which I will color blue. Still within the same graphics, still within the same curvy braces. I put a comma, blue, comma, arrow. This next arrow is going to represent the velocity vector. Start by putting curvy braces. Then put the base of the vector. You want the velocity vector to be based at the point as it moves, right? You know that? We said that before, 2.5 months ago. So I don't put 0, 0. I don't want it to be based at the origin. I want it to be based at C of B. What should its endpoint be at? It should be the velocity vector. It should be really the derivative of C. You could call it C prime, but because I'm not basing it at the origin, I have to translate it to the point where that's moving. I have to add C and C prime for the endpoint of the velocity vector. So the endpoint of this is essentially C plus C prime. Put a prime in here for the derivative. This thing itself, algebraically speaking, the derivative is the velocity vector symbolically. But as far as Mathematica is concerned, and as far as interpreting velocity vectors correctly, you don't want it to start at the origin, you want it to start at the point as it moves. So don't put a 0, 0 first, put the point. Then to get the right endpoint of that velocity vector, if I just put C prime, it would base it at the origin. Or it would, well, it wouldn't base it at the origin because of that, but it would be at the wrong spot, okay? It would be at a weird, hard to interpret spot. You need to essentially translate it by also adding C to B there. There it is, blue. You don't see the arrow ahead because it's too long. Although because as we move toward the origin here, the speed gets slower, the blue arrow will get shorter. So we will be able to see the whole thing. Yep. And at every moment in time, wherever you happen to be at that moment in time, that curve is tangent. That blue arrow is tangent to the red curve. It's pointing in the direction of motion at every instant in time. And does have the right length based on how I've done this. Its length equals the speed at every moment in time. And it's slowing down, so the blue arrow is getting shorter. And then for fun, we can add an acceleration vector in here. Let's color it green. Copy and paste this over here, and just change the C prime to a C double prime for acceleration vector. You want to base acceleration vectors at the point as well. Weird, the acceleration vector initially is pointing that way. Kind of weird. It is true for the curve motion you see here. That is the acceleration vector essentially at time 0. And the entire time, the angle between the blue arrow and the green arrow, well, not the entire time, but most of the time the angle is bigger than 90 degrees, not always. When the angle is bigger than 90 degrees between the blue and the green arrows, what that's telling you is the motion you see in this phase plane is slowing down. It's essentially the acceleration vector of this motion is kind of opposing the velocity vector, causing it to shorten, causing the motion to slow down. It's not always opposing it, which is actually an unexpected thing to me. I would have thought it would always oppose it. For example, right about, well, right about there, it looks like the angle between the blue and green is less than 90 degrees. So actually for the motion in the plane here, at that moment in time, the object's actually speeding up, or the point's actually speeding up. The blue arrow, for the next small amount of time, is actually getting a little longer. But then the angle gets bigger than 90 degrees, and then the motion starts to slow again. That's interesting. I didn't expect that to happen. Do the blue and green arrows have any interpretation of the mass in the spring? Maybe, but if it is, it's not clear what it is. The red arrow has an interpretation. It's, again, pointing at the point itself, whose coordinates, x and d, represent the position and velocity of the mass in the spring. So you could interpret the red arrow. I suppose the fact that the blue arrow is getting smaller is indicative of the fact that the mass itself is coming to equilibrium. It's one interpretation to give the blue arrow. But as far as their directions go and their exact lengths go, maybe you could give it some interpretation of the mass in the spring, but if there is an interpretation, I don't know what it is offhand. To me, this is just a fun way of re-emphasizing some concepts from earlier in the semester. And we could also calculate the speed function as the length of the blue arrow, the square root of the sum of the squares of the derivatives of x and b. And we could integrate it to find the distance traveled function. We could do that kind of stuff too. I'm not going to take the time to do it today. Maybe next Monday we will. Re-emphasizing those concepts. All right, in the remaining time we have, which I thought I'd have more time for this next topic, we're going to start talking about interacting species models. And what I have here are a couple functions that are right-hand side functions for a system of differential equations modeling predator-prey models rabbits and foxes again. Capital R represents the rabbit population, capital F represents the fox population. Probably the rabbits are like in thousands of rabbits, and the foxes are in hundreds of foxes, or maybe even just tens of foxes. These functions are going to be the right-hand side functions for a system of differential equations. So the little f is going to be the right-hand side of the first equation. 2r minus r times f. And the g function is going to be the right-hand side of the second equation, negative f plus r times f. The left-hand sides are going to be derivatives of the rabbit and fox population. Rabbits coming first, and foxes coming second. That's the system of equations, system of differential equations. But these functions that are in Mathematica are going to be the right-hand sides for. This is the little f right here, on the right-hand side of the dr/dt equation. Little f of capital R comma capital F. Little f is a function, capital F is a variable. This is little g of capital R comma capital F. This is a predator-prey model. Foxes are the predators, rabbits are the prey. Ignore Zootopia. And actually, I think foxes don't eat rabbits unless they're really, really hungry. What's going on here? Why is this a possibly valid model? Think about it in the absence of the other population. If you think about the rabbits in the absence of the foxes, capital F is 0, the equation would become dr/dt equals 2r. That's an exponential growth model for the rabbits when there are no foxes, when F is 0. On the other hand, when F is not 0, then you get a minus r times F term. That's contributing to dr/dt in a negative way, perhaps even making dr/dt negative if r times F is sufficiently large compared to 2r. Like if F is bigger than 2, for example. On the other hand, for the foxes, if there are no rabbits to eat, they're starving, their equation is df/dt equals negative f. That's exponential decay. They're dying off. But when there are rabbits, when r is bigger than 0, you get a plus rf term contributing positively to the df/dt equation, to the derivative of the fox population, causing them perhaps to grow. That's the intuitive insights into why this is a predator-prey model. You can also have competing species models, where you've got two species that compete for scarce resources, and cooperating species models, where two species share the environment, and in fact, the benefit of one species benefits the other. We'll talk about those briefly before we end class today as well. But in the time we have remaining, I think it'd be best to focus on Mathematica as well as some big picture ideas. We want to draw the phase plane for this. Do we want to solve the corresponding differential equations? Well, kind of. But if you try to use DSolveValue for the system, it doesn't work. Let's go ahead and try that. DSolveValue. I need to modify things. I got a dr/dt instead of dx/dt, so this needs to be a capital R. What goes here? dr/dt is little f of capital R comma capital F. I've already entered little f, I think, well, maybe not here. Let me enter this. Little f of R comma capital R comma capital F, but Mathematica needs to know that those things depend on t, so I need to type that in there like that. dr/dt equals little f of capital R comma capital F. Don't put the t's on the right-hand side by hand. Do put them in there on Mathematica because these are functions of time ultimately. That's the rate of change of the rabbit population. What about the fox population? Change the capital R here to a capital F. Change the little f here to a little g. Can this solve it for an arbitrary initial condition for rabbits and foxes? Oops. I don't think so. I think it's going to give up. It didn't give up. I think I need to do some clearing of some variables here. That might be the problem. Okay. This TT, I'm not sure what the problem is. Let me quit the kernel. Evaluation, quit kernel to clear the memory completely. Re-enter this first line. Now re-enter this one. Okay, I guess it is trying to solve it for some reason. Okay, maybe you can represent it in terms of non-elementary functions to some degree. I see this product log here. Okay, it's a non-elementary function. One of these other functions you've never heard of before. I do see inverse function here, so it's trying to kind of solve it in a theoretical way, but very nasty. And whatever the case is, it involves non-elementary functions. So essentially, DSolveValue is no help. We can still, however, draw the phase plane. In other words, the vector field. F, little f of r, comma, capital F. Then little g of capital R, comma, capital F. These are non-negative populations, so I should probably do something like this to see a nice picture. It's actually not the vector field, it's the direction field because all these vectors have the same size. Even though you can't find formulas for solutions, based on this picture, you can approximate what they look like. If you have an initial condition, say right there, where R is 6,000 rabbits, and F is about 100 foxes, your solution's initially going to head up this way because of that arrow pointing northeast. Meaning both populations start growing. But as you head up this way, you got to curve to the left if you're going to follow the vector field. And R, the rabbit population, must be decreasing. There's enough foxes now that they're eating the rabbits faster than they grow. You head up here, and you start coming back down. Now the fox population starts decreasing because probably there's too few rabbits. Both populations are decreasing. Towards zero, it seems. Now they're both low. And when they're both low, the rabbit population is free to grow again. And in this model, it's going to come back towards starts. It's going to be a periodic solution. Though that's not obvious from the picture. It could theoretically spiral into something, maybe some stable solution there, some sink. Yeah, there actually could be, but actually for this model they are periodic. Are there equilibrium solutions? Big dots that I should put in this picture? Let's try to figure that out by hand. Quickly here. The big dots, the equilibrium points, which represent equilibrium solutions of the differential equation, the system, where your R and F functions of time are actually constant, are found by setting the right-hand sides equal to 0 and solving the resulting system of algebraic equations. 2R minus R times F equals 0, and negative F plus 2RF equals 0. Solve this system of algebraic equations. This is a system of differential equations. This is a system of algebra equations. Solutions of differential equations are functions. Solutions of algebra equations are points. How do you solve it? It's nonlinear. Well, you do try to factor if you can, and in this case you can factor. You can factor r out of the first equation.
This is an arm here.
You can factor an f out of the second equation. And that is helpful in determining these equilibrium points. It tells you, for example, if both r and f are 0, you get an equilibrium point at the origin.
Where did the 2 come from in the bottom equation?
I don't know. Just was in my head, I guess. Thanks. For some strange reason. Thanks for pointing that out. If r and f are both 0, if there are no rabbits and no foxes, they stay 0. You don't inject them into the environment or kick them out in this model. These equations can also both be 0 if r is 1 and f is 2. Are there any other solutions? Sometimes there can be. No. If r happens to be 0, making the first equation 0, the only way the second equation is going to be 0 is if f is 0. Conversely, if f is 0, the only way the first equation is 0 is if r is 0. Furthermore, if f is 2, the only way the second equation can be 0 is if r is 1. And vice versa, if r is 1, the only way the first equation can be 0 is if f is 2. There are only 2 equilibrium points, so that logic is easy to get confused by. 0, 0, and r equals 1, f equals 2 are the 2 equilibrium points. Let's put them in here. Zero, 0, and 1, 2. There they are. They are special points for the phase points. You can kind of see the solutions here kind of wind around that point. The solutions here seem to maybe approach that point from above and below, but go away from it on the left and the right. These do seem to be important points, and they are very important points. What about actual solution curves? Can we get those in the picture? Again, the DSolveValue seem to be no help. On Monday, we'll use another command called nDSolveValue. N in front means numerical solution. We will approximate the solutions and put them in the picture. But you should understand the idea that solutions follow the direction. See you on Monday.